Welcome back to Networking Explained. In this episode, we're tackling the quiet giant behind everything you do online, TCP IP. It's the layered system that carries your DNS lookups, your TLS handshakes, your HTTP requests, basically every byte you send or receive. Over the next few minutes, we'll peel it back, layer by layer, so it stops feeling like a mystery. So let's start with the actual problem TCP IP was built to solve. Imagine you want to send a message halfway around the world. It has to cross dozens of networks, routers, and cables you've never heard of, owned by different companies in different countries. How does it find the right path? What happens if some pieces get lost or arrive jumbled out of order? TCP IP is the shared rulebook that answers all of those questions, letting any two devices on the planet talk to each other reliably. It really is the foundation everything else sits on. So, if we had to compress all of that into a single sentence, here it is. TCP IP is a stack of protocols where IP delivers packets to the right place, and TCP makes sure that delivery is actually reliable. Think of IP as the address and the route. It knows where things need to go, while TCP sits on top and guarantees the data arrives complete and in order. And that's the key idea. It's layered, with each part doing one specific job. To make all of this concrete, let's use an analogy that genuinely fits. Imagine you need to mail a long manuscript. You split it into numbered envelopes, write the destination address on each one, and drop them in the mail. The postal system routes every envelope independently. They might even take different paths to get there. On the other end, the recipient sorts them back into order and requests any that never arrived. That's TCP IP in a nutshell. The address is your IP address. Each envelope is a packet. The postal routing is IP, and the reordering and re-requesting, that's TCP doing its job. With that picture in mind, let's give the system some structure. The TCP IP model organizes everything into 4 layers, and the key rule is that each layer has exactly one job, only talking to the layer directly above and below it. At the top, the application layer is where your code lives, HTTP, DNS, TLS. Below it, transport handles reliability and ports through TCP or UDP. Then, the internet layer, which is IP, takes care of addressing and routing those packets. And at the bottom, the link layer, Ethernet or Wi-Fi, moves bits across one physical hop. So how do those layers actually cooperate? Through something called encapsulation. Your HTTP request starts as plain application data, then TCP wraps it with a header carrying port numbers and sequence info. IP wraps that again with source and destination addresses, and finally, the link layer adds a frame with MAC addresses for the next hop. Think of it as nesting envelopes, and on the other side, the receiver simply opens them in reverse order to recover your original data. Now let's zoom in on that IP layer, because addressing is what makes the whole system work. IPv4 uses 4 numbers separated by dots, giving us about 4.3 billion unique addresses, which sounded like plenty in the 80s, but we've essentially run out. That's why IPv6 exists, a longer format that unlocks roughly 340 undecillion addresses, more than we'll ever realistically need. Both serve the same job though, identifying a device on the network so routers know where to forward your packets. But getting to the right machine is only half the story. A single computer might be running a web server, a database, an SSH service, and more, all at once. That's where ports come in. Think of the IP address as the street address of the building and the port number as the apartment inside. Port 80 knocks on HTTP's door, 443 is HTTPS, 22 reaches SSH, 53 talks to DNS, and 53432 connects you to PostgreSQL. Same computer, different doors, different conversations. Once you know the right building and the right door, TCP still wants to make sure someone's actually home before sending anything important. That's the 3-way handshake. The client sends a SYN, essentially, "Can we talk?" Their server replies with a SYNAC, "Yes, I'm ready," and the client closes the loop with an ACK. "Great, let's go." Only after those three little messages does any real data start to flow. It's the same TCP step quietly happening underneath every TLS or DNS exchange we'll look at later. Once that connection is open, TCP has four quiet tricks that turn a messy network into a reliable stream. Every packet gets a sequence number, so even if pieces arrive out of order, the receiver can stitch them back together. The receiver then sends acknowledgments confirming what made it through, and anything that goes missing is automatically retransmitted. And with flow control, TCP slows the sender down whenever the receiver starts to get overwhelmed, so nothing gets dropped just because one side is faster than the other. But all that reliability comes at a cost, which is where UDP enters the picture. UDP skips the handshake, skips the acknowledgments, and just fires packets into the network. Fast, lightweight, no guarantees. That trade-off actually makes sense for things like video calls, online games, DNS lookups, or live streaming, where speed matters more than perfection and a missing packet is better than a delayed one. TCP is the careful courier. UDP is the postcard tossed in the mail. So let's pull all of this together by watching what happens when you simply load a web page. First, DNS translates the human-readable name into an IP address. Then TCP opens a connection with its three-way handshake, while IP quietly routes every packet to the right destination. TLS layers encryption on top for HTTPS, and only then does HTTP step in to actually request the page. 5 protocols, 1 click, and notice how TCP and IP sit at the bottom, calmly carrying everything else. Now that you've seen the stack in action, let's clear up a few misconceptions that trip people up. First, TCP IP isn't a single protocol. It's a whole family, with IP, TCP, UDP, and others working side by side. Second, your IP address doesn't pinpoint your house. It points to your network in a rough region. And third, TCP isn't automatically better than UDP. For live video or gaming, UDP's speed beats TCP's reliability every time. One more thing worth mentioning while we're here. You'll often run into the OSI model in textbooks and certification courses. It's a 7-layer framework that's great for teaching and troubleshooting, but it's not what the internet actually runs on. The real world uses TCP IP's 4 layers. Same core ideas, just sliced at a different level of detail, so don't get thrown off when you see both. Now that we've got the theory in place, let's talk about the tools you'll actually reach for when working with networks. Ping tells you if a host is alive, traceroute shows the path your packets take to get there, and netstat, or its modern cousin SS, let you see what connections your machine has open. For deeper work, Wireshark and TCP dump let you inspect real traffic packet by packet, while curl is your go-to for poking at TCP and HTTP endpoints. We'll see most of these in action soon. Before we move on, let's pull the key ideas together. TCP IP is the layered foundation everything else rides on. IP handles addressing and gets packets to the right machine, while TCP makes sure they arrive reliably and in order. Ports then direct that traffic to the right service once it lands. And when you need speed over guarantees, UDP is there to strip things down. Keep these 5 ideas in mind. They're the mental model the rest of networking builds on. So why does any of this actually matter to you? Well, the next time you see a connection refused error, you'll instantly know it's a TCP or port issue rather than a mystery. You'll understand why some requests feel slow. Those round trips and handshakes add up. Security concepts like firewalls and packet filtering will finally click, and you'll see how DNS, TLS, and HTTP are really just layers sitting on top of the foundation we've been building. And if you want to keep building on that foundation, the Networking Explained series picks up right where we're leaving off. Episodes on DNS, TLS, HTTP, and load balancers, each one another layer on top of the TCP IP base. And if security is where your head is at, take a look at SSH hardening mastery over at Dargslan.com courses, because once you understand ports, the natural next step is learning how to lock them down. Before we wrap up, I've got a quick question for you. When did TCP IP finally click? Was it the three-way handshake, the moment the layers stopped blurring together, or when ports suddenly made sense? Or honestly, is some of it still fuzzy? Drop it in the comments. I read them, and those answers shape the next episodes in this series. And that's a wrap. You now understand the layer that everything else on the internet rides on. Every website, every app, every stream. If you want the rest of networking explained, hit subscribe so the next episode finds you. You can also check out dargslan.com for more. Thanks for spending this time with me. I'll see you in the next one.